Good afternoon, everybody, and thank you for introduction. And it's my great honor to have a presentation here. Also, my presentation is entitled as a novel inkjet-printed chipless RFID-based passive fluid sensor platforms. It's very special thanks for NSF for funding this project. So here comes the outline of my presentation. I'm going to briefly talk about motivation and then explain what is the RFID-based sensor, and then integrate RFID-based sensor with a new fabrication method, which is inkjet printing. Then I will present my design, then show you design steps and how does it work in frequency domain. So motivation is pretty simple. There's a lot of sensors around here already, and those are working very well. But however, what if we are introducing some rugged sensor-based systems like flexibilities, wind flexibilities, and what if we should think of the cost as well. So in terms of the costs and the flexibility, we figured out we need a new sensor topology, which is the wild sensor topology for emerging sensor-based systems like this kind of unflexible papers or polymers, or the water level sensor utilizing inkjet printings on paper. So what is RFID-based sensor? Actually, RFID is pretty much familiar to us, and it is everywhere in normal life and contemporary society. So conventional normal RFIDs act like this, give an interrogation signal and return back backscattered signal and like identification code following the modulations. However, what if we integrate sensor capability into RFID tag? Then it will give us a simple structure, which is RFID system is relatively simple, and we can integrate this sensor system into a conventional or pre-built RFID readers. So already, RFID-based sensor demonstrates that it has a lot of broad sensing capabilities, from gas to the temperatures. Also, it's very low cost because it's built on RFID system and good compatibility with conventional sensor networks, which means we can utilize pre-built infrastructures. So it also good compatibility with the additive fabrication method like inkjet printing. Then how does inkjet printing works with RFID-based system? Well, inkjet printing is also very well-known and widely utilized technology in home or in the lab. So it is very low cost, which is very good compatibility with RFID system, because RFID or RFID-based sensor should be deployed. The number of the deployed sensor will be huge. Also easy to mass produce because, well, once it integrates with the roll-through printer, like a newspaper, we can print it in a second more than 1,000. Also, environmental friendly means we don't use any etchant to like wash away metals or something. So inkjet printing doesn't have any byproduct. Also, faster prototyping, like fast is to mass produce, they are same meaning. So if we integrate RFID technology, which is low cost, which should be low cost and large scale implementation, then inkjet printing can magnify this requirement of RFID, and then we can take advantage of sensing capability of RFID-based sensor. So let's talk about inkjet printing technology a little bit more. Recently, there are lots of electronic ink, which including nanoparticle inks or polymer inks. PBPs, SUA, PMMA, and PDOT, which is the conductive polymers, can be printable utilizing normal printer, as well as CNTs and silver nanoparticle, graphene, coppers. They are also fully inkjet printable. And it's cost efficient because we deposit exact amount of ink on exact desired positions. So there's some examples of the inkjet printed electronics, which is the luminescence, and which has a very fine resolution, which goes down up to 240 nanometers. Then our interest is metallization. How do you metallize on flexible substrate like a paper or polymers, utilizing fully additive process? So one method is utilizing silver nanoparticles. The reason for choosing silver nanoparticle is silver is all the most conductive material. So normally, if we make a bulk metal into a nanoparticle like this, the conductivity goes low, almost 1/10. If you make it very well, it goes up to 1/5 or like that. So taking into account that we use silver nanoparticle because it has the highest conductivity in the world. So it is inkjet printed on glass, and its roughness and electrical conductivity is measured, which is very good, 11 to 15 nanometer, which is almost the same as the nanoparticle size variation. Also, conductivity is compared to bulk iron or nickel. Then I focused on what is good material for RFID-based sensor, because that is one thing to lower the price. However, this substrate should satisfy these things, flexibility and compatible with fabrication process, because we should inkjet print on that paper and that substrate. Also, durability and cost and environmental effect for the future applications and the sustainable sensors in the environment. So I summarized famous and very popular inkjet printable materials here. Well, paper and porcelain, they are same paper. But paper is the cellulose-based paper, which you can have it now. And porcelain is the synthetic paper. Normally is made from the polymers, and the application is for your card or name tags in conference area. And LCP is very famous and popular material for low loss, high frequency material. And acetone, which is polyimide, is also popular material for the mechanical area and the high frequency area too. But in this case, I focused on printability and the cost. So paper and porcelain cartons shows a very good printability. LCP also very good in inkjet printing, but compared to those three things, they are relatively low. In the cost, paper, needless to say, very low cost. Next is porcelain and carton. In this presentation and this proposed design, well, we utilize carton because it shows a good printability and thermal durability, as well as, well, it's relatively high, but we are going to use a high Q-factored system like this, high Q-factored microwave circuit. So we choose a low loss material, so we decide to utilize carton. So whole sensor geometry is 12 centimeter by 12 centimeter. This is the receiver antenna and transmitting antenna, or vice versa. And this is the gap-loaded tunable filter. So I will discuss how does simple structure work working as a sensor. This is the operation principle. We utilize a dual-polarization antenna in this way. Give a signal in horizontal, utilizing just sweep the carrier frequency. Then this tag receives the horizontal signal, then passes through the filter and radiates back in horizontal way. So utilizing the isolation of two antennas and the polarization, we can take advantage of sensing capability like this. If we send the same level of signal in this way, in horizontal polarized wave, the received power will vary depending on frequency, because the sensor, the tunable sensor, has a different passband depending on depending on the load, depending on the passband of filter. Passband of filter, we can expect the peak of the received signal in this way. So this is the detailed picture and the geometry. Actually, this is not inkjet printed yet. In this presentation, we utilize a board level design utilizing Rogers material, and we made a metal circuit. We made a filter here on top of the Rogers material utilizing milling machine as for the demonstration of proof of concept. So it is tested utilizing VNA. It has a passband at 2.6 gigahertz at the without any loading, without 2.4 dB as insertion loss. Then, by loading the sensing materials like water or acetones, we can expect huge amount frequency change shift. So depending on the dielectric constant, we can see a huge frequency shift, about 400. The sensing capability is about 400 megahertz, and depending on the dielectric constant, we can mapping the frequency shift, which material is loaded on the sensor. So this is the designed antenna, broadband monopole antenna, which is loaded with circular disc. It will give us a broadband which enough to cover our sensing capability, 2.2 to 2.6 gigahertz. And this antenna has a broadband and the omnidirectional radiation pattern with a 3.0 dBi at 2.4 gigahertz. And then next step is we should verify how this sensor working. So we put the antenna, broadband antenna with the tunable filter together and connect it to VNA here. And the sample fluid, such as acetone and water, was loaded on the filter. Then surprisingly, we can see the exact, almost same resonance point. Then it means, well, this is one-port network. This ping means, well, it radiated from the outside. This measurement was measured in anechoic chamber, and then we can expect 400 megahertz shift with water and 200 megahertz shift of the acetone. So this is the inkjet printed sensor on Capton. Well, this is under developing now, but you can see how fine feature it is. Utilizing milling machine, we got about 300 micrometer as a gap. By utilizing the inkjet printer, we got 280 micrometer gap, which means the lower insertion loss with the high efficiency for the feature for the filters. So for the measurement, we design dual polarized reader antenna in this way. This is slot antenna and the broader side radiation pattern to get a more higher gain. Then the measurement and simulations are very good, and it has a very high gain at 2.4 gigahertz, and it has a very high isolations. So during this presentation, I covered what is RFID-based sensor and introduced how do we utilize inkjet printing as RFID sensor, and then basic operation principle of the proposed system, and then lastly, I presented the integrated and fully inkjet printed RFID chipless RFID sensor. Thank you for attending, and any questions will be welcomed. Thank you.